Yeah, let's do the next step. Look at the next controller. A student had found this controller in a paper nearly 30 years ago. This paper was developed by a scientist at the Technical University in Chemnitz, just 2 years after opening the borders. Okay, this file. The file is available in the Moodle course. I open the Moodle course, show you where you can find it. There is a folder Docs. In Docs you can find some papers. I'm not sure if I can publish these papers, so I think I should deactivate the papers just after some hours. So, but note that this is a 30 years old publication. You can look at it, German one. Here you can find the paper out of a book. It's also 30 years old. I think copyright is now not available. The German theory of dead beat controller from my colleague Mr. Baumann is just publishable, no problem. So I think look for these papers, and then if you want to go deeper into the details, you can do this. I have offered the sources for this. Okay, note the theory. I can just very shortly show you what is behind the orientation controller. That is a predictive controller introduced in the next chapter in more detail. So I have not really go deep into the theory of this controller, because I've just take the algorithm out of the paper, program it, and play several years with this, with at many positions very good success. First, this controller is designed using the problem of limitation of the output of the controller. So there are no problems with the controller outputs which are limited. This controller can also work with an unstable process. So an unstable process can be controlled not with a PID, not with a dead beat, but with an orientation controller. So these are two big advantages. On the next page you can find a third big advantage. You need the process step response invariant filter function. So this is a result of the online RLS identification method. So this controller can also be adaptive. That means you automatically measure during runtime or before or anywhere, measure the f of z of the process, and then the design of this controller is simple. I just very quickly go through this design. This is just covered, you see, copied out of the student paper 30 years ago. I don't want to spend too much time to put this into the formula editor of Windows, of Word. But here you see, this is the controller algorithm, the controller transfer function. Here, this is the orientation controller. In the paper, they used G's and H's as parameters. It doesn't matter. The degree of the controller is M. That means the process degree depends. The controller degree depends on the process degree. Here the process is given with the A's and B's, very similar to my previous papers, degree M. And then in this publication there is a correction factor calculated. Note that the names here are different. I just take these names because these names reappears in the code at the end of this chapter. So I don't want to change this, otherwise I have to change also the code. So the output of the process is now Y, the input of the process, output of the controller is U. So this is the actual measured process output. These are process outputs steps earlier, and these are controller outputs some steps before. And the ASMBs are just the process coefficients. Okay. Note that here a prediction is made. What is a prediction? This is the process output, and this is a process output at position K, and this is a process output at the position K plus 1. So with this algorithm, this program calculates an expected process output using the actual and old controller output values. These are old process output values, old controller output values, correction factor, and here the process parameters. So this is the algorithm equation to calculate a prediction. This is the idea which is explained in the next chapter 9.7 in more detail. And with this prediction, you see this prediction is used in this algorithm. Is if R and D are 0, then here this is a prediction value which is used to calculate now the actual controller output. With some equations, you see you have to do some work in the computer to program some lines. I have just do this step by step. You see the program code in Windows C#. You can look at it. This open source program. You can find this code just very near to the mathematical description, and you see in the controller algorithm for this is using say 20 lines, and then you get the controller output of the orientation controller. So this is the code with some documentation, and that's all what I can give you as information for the orientation controller. I want to do the next step. I can now demonstrate this orientation controller. Note there is some disadvantage I will also show in the demonstration, which is the disturbance behavior is not good. So the disturbance cannot be compensated completely. So there is a control error in disturbance. So this is very good used in reference behavior, but yeah, in disturbance behavior, orientation controller is a little bit poor. Okay, let's go into my simulation program. I show you the settings. The settings are identical to the settings of the last demonstration. My process is K is 2 and 200 milliseconds, 100 millisecond, 20 millisecond sampling time. I want to show you the ideal version of these algorithms. So hardware simulator is okay. Then the controller design is also made with K is 2, 100 millisecond, 200 millisecond for 2PT1. Ideal algorithm is designed, so I send these controllers to the algorithm with this button, and note that here the deadbeat controller has our 28 value from our manual calculation. What we can also look at, what we have not done is the coefficients of the deadbeat nu plus 1 is 10 here, and you see this 10 is larger than our limitation factor 10, so also this controller will be limited. You can also check the parameters of the orientation controller. There are of course also some values, but here you see larger than 10. So the question is, how can this controller react on a controller output limitation? I will show you. So I send all these controllers to the control box, and now I go to the adaptive control box. Here the parameters are ideal, limit is enabled, plus to minus 10 volt. Unit step function should be selected, and I want to have the reference behavior. So this signal, this amplitude goes to the desired value. Later I will show you the disturbance behavior with this radio button clicked. Okay, in the last video I have shown you this free PID. I have not explained what this is. Here you see there is a PIDT1. This is a PIDT1 with design 1. This is design 1 with anti-wind-up function. This is a free PID, and with this button you can select parameters of this free PID. Look what you can see here. This controller is designed with step depth 5 and sampling time 20 milliseconds. And here with this radio button you see this is the design 1 sharp. But of course you can change your values, convert into other controllers, calculate new controllers, no problem to do this. And these values then are copied to the algorithm with this button. I first deactivate anti-wind-up to show you the 1 sharp controller without anti-wind-up. So this you have seen. You have seen the deadbeat controller, unlimited and limited. And now I want to add the orientation controller. But first I want to show you that the limitation will be stronger if I increase the amplitude. So I want to show you first the PIDT1 design 1 with a unit step at the desired input, and the result is this. You see, a little bit different to that what we have seen in last demonstration. The design 1 controller has here a small overshoot, a strange behavior here, could be faster, but this is the case. And now I increase the amplitude, I double the amplitude. That means the controller output must be larger to get larger process output values, and the limitation effect will be stronger. Next step is I go to the amplitude 5, run in it, then you see the PID here has no overshoot, small overshoot, large overshoot. So the limitation effect caused a wind-up mechanism. So the overshoot will be larger and larger. Let's check what the anti-wind-up mechanism described also in the paper, in the lecture, in some old videos, what anti-wind-up mechanism could do with this very large amplitude. I have activated this, and you see, okay, here the response is a little bit slower, but the overshoot is smaller. So this is maybe better or not, I cannot say it. So the PID has some problems with this limitation. Let's look what a deadbeat will do with this large limitation factor. You should note the first moment, this 5 volt, if the process output is 0, the 5 volt goes directly to the deadbeat controller and is multiplied with Q0. This is nearly 30 times 5 is 150. So the controller wants to have 150 volt and gets only 10. So the limitation factor, the ratio of that what he wants and that what he get is 15. Result is, you will see a very large overshoot. Yeah, deadbeat controller with this strong limitation effect has very worse behavior. Now I show you the new one. That is the orientation controller. I have presented in chapter 9.6, and yeah, I start with deleting all curves and unit step response. And then you see this controller has a response which is rather good, nearly no overshoot. Now I increase the amplitude. That means the controller output will be limited, and you see no overshoot. This goes longer and longer, and you see here in this case, if I do this with 5 volt, well, the PID has some problem. Also, the controller output of the orientation controller is really without any overshoot, exactly lying down on 5 volt. So you see this controller is much better. And the reference behavior, like the other controllers, again, the PID with anti-wind up compared with this controller was in this situation here slower, overshoot, settling down takes a long time. So here you can see the orientation controller is really much better and is a winner of competition if you compare both controllers. Yeah, so this is the first demonstration of an orientation controller which is well adapted to the controller output limitation. The same as if I go over to the much stronger case. If I now limit to 0, that means in a heating system I can only heat, not cool, or in a driving system I can only accelerate, not brake with the motor. If I have this case, then you will see what happens with the controllers. First the PID with anti-wind up, unchanged, so there is obviously no negative input. And now orientation controller, which is also unchanged, so the limitation to the negative values is also has no influence to the good behavior of an orientation controller, and no negative influence to the PID controller. That the deadbeat here doesn't work properly in this case we have shown in the last video. So I close this demonstration of the orientation controller with the poor disturbance behavior. So I delete all curves. This is a delete all curve button. It's not visible if the room of my video here is limited, so I have to shift in this region. Now I want to demonstrate the disturbance behavior. Then we have no problem with large amplitudes. We can also go back to the unit step response for the disturbance. The orientation controller, you see, has now a constant output, cannot remove the disturbance properly. The PID T1 design 1 yeah, that's good. What's that? Okay, that is the question of, if I have a disturbance and cannot go to negative values. Okay, also, let's go with negative values to understand, run in the process. Okay, with the negative value, you pull it back to 0. That's the red curve. I'm laughing because I have not expected this curve. I have not expected this curve. What is with the deadbeat controller in this case? Deadbeat can remove, but can the deadbeat also remove if we have a heating system? Let's check. Oh, he can do. And what is with the PID without anti-wind up? This works. So you see deadbeat and PID with negative values is working. Why an anti-wind up version doesn't work, it's at this time not so clear. I think I could, yeah, I see this. It is an anti-wind up mechanism. So I just show this again because this is also unexpected by myself. I have a disturbance response. This unit amplitude PID design 1 can remove disturbance. Then I, in the case of no negative values, now I click to anti-wind up function, and now you see then a PID including anti-wind up function cannot remove the disturbance because I guess what happens in the algorithm, the controller output want to be negative to pull it back. Then the controller detects a limitation, and in the case of limitation, the integrator is deactivated. That's a trick of the anti-wind up mechanism. In this case, the anti-wind up mechanism works not good. So you can see you have to test your algorithms, the combinations of the algorithms, sometimes to get problems with some combinations. I never have seen this. Sorry for this. That is new for me. So I'm astonished. I can understand it. I can explain it. And okay, this is a case where we have to work a little bit on it. Yeah, to say, okay, if we have heating systems and disturbance responses, be careful with the anti-wind up function. Yeah. Last experiment is I check what happens with the anti-wind up function in the design 1 sharp version. Let's look for this. Without anti-wind up, 1 sharp version, step depth 5. Close is working properly. Takes a little bit more time because the step depth here is not so large than this. This is a step depth 6. That is a step depth 5. Now I check what the anti-wind up mechanism is doing. Sorry, I should copy it, close, run, init process, disturbance, step response, same procedure. So yeah, be careful with anti-wind up in the case of limitation to only positive values. An anti-wind up mechanism leads to a disturbance control error. Okay, interesting. Okay, but I think you have seen the orientation controller in the demonstration of the adaptive systems. You have seen that the orientation controller can also control unstable processes. Let's show this a little bit. I change to a negative time constant in my process curve. So I make a new process. You see here in my hardware simulator. Now I click on the minus sign. This gives a negative time constant, gives new A's and B's. Say OK. Then I do the same here. The 0.2 time constant is negative. I make a controller design, send it to the curve. The PID controllers could not work really. So here you see negative Q0. It could not work. Could not really work. A PID cannot do the job. Let's do this. The init is, I set all signals to 0, but a small change here could lead to an explosion of the output of the controller. But I want to see now the reference step response. You see, yeah, PID could not stabilize, deadbeat, init process, run, could not stabilize. Orientation controller does nothing. Okay, run. Nothing happens. Okay, why this? I have seen this working, but today I have a not successful demonstration. Sorry for this. Should work. Why does this not work? So I think I see. Okay, I see. I need negative values to stabilize the pendulum. I think this. Yeah, sorry for this. The orientation controller could do this. I know this. But of course, he needs negative output to control this system. And if I have no negative outputs, of course, no controller can do the job. But you see, the orientation controller, I can do this again. Init process, run, init process, start. You see, in spite of unstable process, the reference step response of this system works properly. The orientation controller can really stabilize an unstable process to a stable closed loop system. Okay, so I think you see, impressive controller, 30 years old. Code is available if you want to use it. Play with this. C# code is programmed if you have questions for this and you want to implement this in another computer language and you have problems, I can help you. Okay, so far stop the video.